Welcome back to Chapter 3. Today we're going to be looking at Section 2, which is on linear functions. In the last section, we saw what functions were as opposed to relations, and now we're going to focus in on linear functions. As the name might suggest, linear functions are functions which would be graphed as a line. So this is very similar to what we were doing last chapter. We will see the equations of lines again, but we'll look at it at a slightly different angle and we'll focus on some different stuff. So our learning target for today, I can identify, evaluate, graph, and write linear functions. So graph and write linear functions, that's what we were doing last chapter. The evaluate, we were doing it last chapter, but it's the same thing. Slight different notation, but it's the same thing. Um, so first of all, we have function notation. So if we have a linear equation, just y equals 5x plus 1, it's a line, 5 is the slope, 1 is the y-intercept. Function notation, instead of using y, we use something different. We give it a different name. The generic name, since it's a function of x, the generic name is f of x. And this is pronounced, as I said, f of x. And that would equal 5x plus 1. So all function notation is f of x equals y. That's all that is. Why would we use f of x instead of y? We do that for a couple reasons. One, because it shows us what our variable is. Our variable here is x. It's a function of x. The other reason why we will use function notation instead of just y equals is there will be times when we will have multiple equations. So we could have y equals 5x plus 1, and so that's f of x equals 5x plus 1. We could also have y equals negative 3x plus 2. And so we could give that one a different name. We wouldn't call it f of x. The f function is taken. The next name we usually use would be g of x, would be negative 3x plus 2. We use f for function. Why would we use g? Because it's the next letter. That's really the only reason. The third function a lot of times would be h of x. Now, we don't have to use those letters. We could use any letters. And when we have an equation that has some meaning, we would use something that has a meaning. For example, when we have the circumference of a circle, with respect to the radius, c of r would be 2 pi r, because we have the circumference based off of radius. That's one of the reasons why we do it. Another reason why we like using function notation is when we go to evaluate. If we wanted to evaluate this for x equals 3, we would just replace all the x's with 3's. So this would be f of 3 equals 5 times 3 plus 1. We just plug it in. Now, one of the things that people get confused about, they see this f of 3 right here, and they think that's f times 3. It is not multiplication. That's just part of the name. It will not be separated at all. You will never have f equals something. It's always f of something will equal something. But when we do this, so 5 times 3 is 15, plus 1 is 16, so we get f of 3 equals 16. This gives us our ordered pair. It's not just y equals 16, Because, yeah, sure, y does equal 16, but y equals a lot of things. Y equals 16 when x equals 3. That's what this says. It gives us the ordered pair 3, comma 16. And so evaluating for a certain number just means plug it in. And again, f of 3 equals 16. If we wanted to evaluate for x equals -2, we would have f of -2 equals 5 times -2 plus 1. So f of -2, 5 times -2 is -10, plus 1 is -9. So we have f of -2 equals -9. F of 3 equals 16. It's not y equals 16, y equals -9. It's like, well, which one does y equal? And then we could also say, like, all right, well, that was f of 3. How about g of 3? What's g of 3? Well, that uses this other equation here. So we'd have -3 times 3 plus 2. So g of 3, -3 times 3 is -9, plus 2 is -7. So f of 3 is 16, g of 3 is -7. We can plug the same value into the different equations. If we were just using y equals and y equals, it gets very confusing when we're trying to say what equation we're dealing with. So that's one of the main reasons why we like to use function notation. It gives our equations, it gives our functions a name. And the f of x or g of x or h of x or whatever just replaces the y. It replaces that output, the dependent variable. And everything else stayed the same. So we wrote it in function notation. That's what we did right up there. And then we also evaluated for a certain value. So you're going to try this one. And this problem should not take very long. I mean, you're going to pause. You could go make yourself a sandwich if you wanted to, but the problem itself shouldn't take very long. So we have y equals -2x minus 3. You're going to write it in function notation and then evaluate for x equals 4. All right, so pause your video, get a pencil and paper, do this. You're going to keep your pencil and paper. You're going to have a couple more problems to do here. When you're done, play the video and check your answer. All right, so go ahead and pause now. All right, how'd you do? Did you pause it or did you just watch through the pause? Go back, pause it, actually do it. This is an important part of the learning. Oh, you have it, it's super easy. Great, write it down. If you don't have it, it's not super easy. That's even more reason to give it a try. So if you have not yet paused it and done it, do it now. All right, so we're going to write in function notation. We can use whatever name we want. We'll just use f of x. So we'll say f of x equals -2x minus 3. That's in function notation. Now we're going to evaluate for x equals 4, which means we want f of 4 equals -2 times 4 minus 3. So f of 4 is -2 times 4 is -8, minus 3 is -11. How'd you do? Did it work? One of the problems here that people run into, aside from trying to divide by 4 to get f equals something, which I know that no one did because I told you earlier you don't want to do that. One of the mistakes people make here is that -8 minus 3. People like to say -5, but you're at -8 and you're going another 3 negatives, so it gives you -11. So that's function notation and evaluating. We can write linear functions. Writing a linear function rule, the rule is just the equation. So if we have a table of values, the first thing that we're going to do is we have to check to make sure that it's linear. And this is going to be good because it's going to get us a value that we need anyway. To check to see that it's linear, we're going to see how to get from each of these. So to get from 1 to 2, that's just plus 1, 2 to 3 is plus 1, 3 to 4 is plus 1. All right, and then also how to get the y's. 17 to 32, now that's a little bit tougher than just plus 1. Instead of thinking, all right, 17 plus what equals 32, go 32 minus 17. Oh, that's 15. 47 minus 32, 15. 62 minus 47, 15. You notice anything here? Hey, all these things are the same. It's going up by 1 each time. It's going up by 15 each time. Being that they're the same, that means that this is linear. In fact, more than that, the slope will be the change of y divided by the change of x. The slope is going to be 15 over 1 in this case. Now, it is possible to have them go up by different amounts. Let's say that we skipped 2 in the x's. We would have skipped 30 in the y's. And so when we divided, it would always come out to be the same. It would come out to be that constant slope. It looks like you don't have any of that right at the moment, but that is something to be aware of in the future. It's this piece that you want to be the same for everything. So we have a slope. So we had to do that to find the slope anyway. We have a slope, so we have y equals, but instead of y, we're going to write it as a function. So we're going to have f of x equals, and then the slope m is 15x plus b. We've dealt with this. This is slope-intercept form. We could do this using point-slope form if we wanted to, or we can just plug in a point. Let's choose 1 and 17. So the y value is 17 equals 15 times 1 plus b. 15 times 1 is just 15. So let's subtract the 15. Subtract the 15, so we get 2 equals b. Plug that back in. F of x equals 15x plus 2. There is another way you could have done it. Being that it was adding 15 each time, the y-intercept is when x equals 0. Well, that would be like the next one over here. So what if we went 15 back this way? Instead of adding 15, we'd subtract 15 to get 2, which is the same thing we did anyway. So there are different ways of getting there if you have a table, and that works, being that we are right there at 1, but that won't always work, at least not as easily. For instance, this one. I'm going to erase my slope here a little bit. This one. We're going up by 2 each time. And here, 2 to 10, that's going to be plus 8. 10 to 18 is plus 8. 18 to 26 is plus 8. So our slope is going to be the change of y over the change of x. Now, one of the common mistakes here is to go 2 over 8, because in the table it already almost looks like a fraction. You have to flip it. It's the y's over the x's. So we have 8 over 2, which will simplify. 8 divided by 2 is just 4. So we have the slope. For the y-intercept, if we tried to just go backwards 1, we'd get to an x equals negative 1. And so, yes, you can work your way around that, but again, that's nice because we're at like x equals 1. If our values were all like starting at x equals 15 or x equals 370 or something like that, that's not a good way of doing it. So just plug it into the equation. F of x equals 4x plus b. Plug in one of our points. How about 1, 2? So 2 equals 4 times 1 plus b. 4 times 1 is 4, so we can subtract 4. So that's negative 2 equals b. Plug that back in. F of x equals 4x minus 2. There's the linear function rule for the second one. All right, do you think you're ready to give this a shot? I think you are. It's going to be basically the same. You can follow my steps right here. I mean, it's not like this goes away. So your table, you have x goes 1, 2, 3, 4. Y is 1, 4, 7, 10. All right, so find the differences in the x's and the y's. Find the slope, make sure it's y's over x's. And then write the linear function rule. All right, go ahead, pause. When you're ready, push play again. How do you think you did? All right, well, let's try this. I hope you did it. So the x's are all just going up by 1s. The y's 1 to 4, that's 3. 4 to 7 is 3. 7 to 10 is 3. So our slope is 3 over 1, which is just 3. So we can plug it in. F of x equals 3x plus b. We can plug in 1, 1. 3 times 1 is 3, so we can subtract 3. 1 minus 3 is negative 2 equals b. Put that back up there. So we get f of x equals 3x minus 2. Is that what you got? I hope so. If it's not what you got, did you see where you went wrong? Self-assessment. All right. And finally, for today, we're going to analyze a linear function. So first we're going to make it, we're going to graph it, and then we're going to see how much sense it makes. So our problem here, Tamika records the outside temperature at 6 a.m. The temperature increases by 2 degrees every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? So she records the temperature, and at 6 a.m. it is negative 3 degrees Fahrenheit. We're going to start the day times 0 equals 6 a.m. We have it increases by 2 degrees Fahrenheit every hour. That's the slope. Remember, the slope is the rate of change. It increases 2 degrees Fahrenheit every hour. That's 2 degrees Fahrenheit per hour. That's a rate. And so that's our slope. And it increases. This is an important word here. It increases. If it said decreases, it would be negative 2 because it would be going down. But it's increasing, so it's positive 2. We're starting at 6 a.m., so we have our y-intercept is negative 3. We can just write the equation here. We'll go f of x. You don't need to use f of x. You could use t of t, the temperature at the time. That's an annoying one. We'll just stick with f of x. Equals our slope, 2 times x. Then our y-intercept is minus 3. So we can graph this. This is just a linear equation. So if we graph this, we have negative 3 is our y-intercept. So we can put a point there. And then we go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And you can keep that up. It's not perfectly straight, but it'll work for what we're doing. So we can graph it. It looks like a line. We can also find what will the temperature be at 2 p.m. So we're going to have to plug in a value, but we're not going to plug in 2 because we're starting at 6, and so 2 would just be 8. So 2 is 8, so 3 would be 9, 4 would be 10, 5 is 11, 6 is noon, then we need another 2 hours, so it'll be 8 hours after 6 a.m. that we get to 2 p.m. So 2 p.m. is going to be 8 hours later. So we're going to be plugging in that 8. Sorry, I underlined the 8 and it looked like I crossed the L, made it a T. 8 hours tater. So we're going to find f of 8. And so that's 2 times 8 minus 3. So f of 8 equals 2 times 8 is 16 minus 3 is 13 degrees Fahrenheit at 2. So obviously this is a cold day that we're talking about here. I mean, it started out at -3, so this is not a nice summer day. Does 13 degrees Fahrenheit seem like a legitimate temperature? Sure, it seems like it could be okay. Now, a question though comes up. Does using a linear function realistically represent the temperature for 0 to 24? So that would be for a full day. Does this linear model, this linear function, does it represent the temperature? Is it going to keep increasing by 2 degrees every hour for the full day? I know I've had questions like this before, and a lot of people say, yes, because it's linear. It's like, no, we have to take a step back from the function and look at what's going on in the situation. We have the temperature of a day. Does the temperature of the day keep increasing all day long and then throughout the night until we get to the same time the next day? No, at some point in time, that temperature is probably going to go back down. Like, it wouldn't make sense to keep using a linear temperature for the full day. It might work for this short period of time in the day, but when the sun goes down, like at 10, 11, 12 at night, the temperature's probably going to fall again. So when you have an equation, especially if it's something that is describing a real system, you want to always think, like, does this make sense to keep going? I had a question on a test for the past number of years where it was talking about a baby whale was growing at like 50 pounds a month or something. Are they going to keep, like, they did that for the first 6 months. Are they going to keep doing that for their entire life? And people be like, yeah, because it's a linear, it's going to keep going up. It's like, no, at some point the whale is going to reach its maximum size and it's going to stop growing. I mean, even if you don't know anything about whales and you think like, well, I don't know, maybe they do grow for their entire life. At some point it's going to die and it's going to stop growing. So you really need to pay attention when you have an actual situation. Like, will the equation itself keep going? Yes, the equation itself will keep going. And like the ones we had on the other slides that were just equations, yes, they'll keep going that way forever. But just because something is linear for the little amount of time that we're looking at it at, doesn't mean that it will continue to be that way forever. You just have to use judgment in those types of questions. And the questions are typically pretty obvious that they want you to think like that. Like this part of the question, I mean, they use the words like, realistically, is it going to do this? And so that's just a clue to get you to think about it in terms of the actual situation and not just the equation. So with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.